fast charging of electric vehicles. Let us have an introduction about what are the types of batteries which are used in electric vehicle. I had seen the pamphlet, and I think there was a session on the types of batteries which are used in electric vehicle. Just we will brush upon the types of the batteries which are used, because fast charging depends on the type of battery which we use in the electric vehicles also. So now, as we are aware, there is a tremendous growth in the electric vehicle sector, because the electrification is happening not only with respect to the cars or two-wheelers. It applies to all categories of the vehicles which are used, whether it is heavy-duty vehicle or whether it is the trains or the trams or the buses. So future is going to be the electric vehicle. So though it is very easy when we say that the electric vehicles are popularly, or what to say, the growth of electric vehicle is transcending, there are challenges which are accompanied with the growth of electric vehicle. So we will have a quick look into. Now let us have a quick look at the what is the trend in the electric vehicle, what is the growth rate, and future what will be the demand for the electric vehicles, and as an electrical engineer what role we have in contributing to this field. So if you look at this survey, like whatever the data which is taken 2024, we could see the trains which were electrified, that is the electric locomotives which were limited in number. Now, so now we look at across the globe what is the rise in the electric vehicles in the 2024, we can see almost it is touching 20 million electric vehicles, and in future it is going to be more. And here we can see what is the market size in the 2025 to 20, that is this is the estimated market size. Uh, I think I can come there so that I can zoom some images as and when. So here we can see what is going to be in $1 million, the investment in the electric field and the electric vehicle field, and how the market share of electric vehicles is. And not only across the globe, in the India also, if we see this is what the plan is. So according to the Smart Grid Mission of India, so we need to have the electric vehicles, the market share is going to be. So in India, if you see, the growth is going to be nearly 50%, and 50% growth is very huge. Even in 5-year plans, we will not have anything which grows by this percentage. And when the number of electric vehicles are produced in the market, we need to have proper supporting facility. What is proper supporting facility is, as we know, when we talk about electric vehicle, we need to charge the vehicle. There has to be sufficient charging stations which have to be built. So now if you see across the country, so we do not have much charging infrastructure. If you take in Chennai itself, hardly we have 4 to 5 major charging stations, isn't it? Then how do we charge the electric vehicles? And when we talk about the charging of the vehicles, so we need to enhance or upgrade whatever the facility we have in respect to the charging infrastructure. That is one major challenge. And when we talk about charging, we know like what is the difference between the electric vehicles and IC, the vehicles which are driven from IC engine. So IC engine we will be able to have long mileage. So when we talk about this thing, one is the charging infrastructure, and when we have lot of electric vehicles which are penetrating the market, how do we handle them? So now when we talk about the charging infrastructure, we know like how much time it will take to charge the mobile. So we know the ampere hour rating of the mobile batteries which are used, and then you think of the charge like whatever the battery rating which are used in the electric vehicle, how much power they have to deliver and what mileage we get. And the major difference between like the cars or the vehicles which are driven from the IC engine and electric vehicle is with respect to the torque handling capability as well as the mileage what we get. IC engine, as we are aware, depending on the capacity of the vehicle, the mileage, and depending on what type of fuel is used and what is the capacity, we will be able to drive longer distance, but that is not possible in case of electric vehicle. Right now, whatever the vehicles which are available, depending on the battery life, they can run up to 300 to 500 kilometers, not more than that. 500 kilometer also only it is possible when we have lightweight battery. So those challenges we are going to discuss in today's session. So please stop me wherever you want to discuss or know more information. When we talk about charging of electric vehicles, there are three ways in which at present the electric vehicles are charged. One is the battery swap. So what we do in battery swap, we just go to the charging station. We just replace the empty battery with already charged this thing so that we can save the time. The other one is plug-in charging. So what is this plug-in charging? We just plug in externally and then allow the battery to get charged, and then depending on what type of charging it is used, it may take several minutes to several hours to charge the battery completely. Then we have wireless power transfer. There is a lot of research is happening in wireless power transfer for electric vehicles. Even we have developed a prototype which is patented based on this wireless power transfer for electric vehicles for Indian roads. So these are the major three ways of charging the batteries of electric vehicle. Now, with that brief introduction, now let us see what is the need for fast charging. Before that, as I said, we will have a brief introduction about what are the types of energy storage devices which are used in electric vehicles and in what way the electric vehicles will be able to perform better than the IC engine. IC engine, we know the major drawback of IC engine is emission of carbon dioxide and then the other pollutants which will be oxides of nitrogen, so that will pollute the environment, and depletion of fossil fuels. For that, in order to move towards greener environment, we go for electric vehicles. So now moving on to the electric vehicles, the energy storage system, usually the batteries, they are very much essential for all types of electric vehicles. And we have following types of electric vehicles. You would have heard of it, completely or pure electric vehicles which are driven from the battery. And we have hybrid electric vehicles. We also have a variant of hybrid electric vehicles which will be plug-in hybrid electric vehicle. So moving on to these are the conventional vehicles which are driven from the gasoline, that is the petrol or diesel engine. So now how the power transfer happens? We will have an IC engine, the power which is developed that will be transmitted to all the wheel axle assembly. The power may be given to the front wheels or it can be given to the rear wheels, depending on that we have front wheel drive and rear wheel drive, or if the power which is produced from the IC engine, if it is being delivered to all the wheels, then we call it as all-wheel drive or four-wheel drive. A four-wheel drive, a four-wheel drive can be converted into all-wheel drive or it can be converted into two-wheel drive. We will have a controller configuration to have transition between four-wheel drive and two-wheel drive. When do we prefer this two-wheel drive? When do we prefer this four-wheel drive? Whenever we have frequent start-stop. When we have two-wheel drive, the power will be given only to the front two wheels or to the rear two wheels, depending on whether it is front wheel drive or rear wheel drive. When we have the power which is being transmitted to all the wheels of a vehicle using the gasoline, that is the petrol or diesel, then what happens? The control will be easier, and then the weight carrying capacity of the vehicle, it all depends on what is your engine capacity, where the engine is placed. If the engine is placed at the back side, then we cannot have proper pull. That means against the gradient we will not be able to move. So now you imagine, so here if the engine is placed, we will not be able to have a pickup. That means that kind of engines cannot be used for heavy duty or like if we are traveling in a hill station. Now you imagine the battery which is huge, like what to say, it occupies more space. If that is placed at the railway, then we will not be able to have a proper pickup. That is one problem. Then what is the solution which we can have is we have to reduce the battery size. If the battery size is reduced, then we may not be able to get the expected mileage. So, and if the battery size is reduced, if you want to travel for longer distance or to get the bigger power in terms of the torque, how do we address that issue? That is also one concern. And another research area where it is open is like if the electric vehicle, if they have to travel in a constant slope, let us say it is more than 80-degree slope, then still they are not able to address those issues with electric vehicle. If somebody is interested in pursuing research in that area, you can take up your PhD work. So against the gradient, if the electric vehicles have to move, then what kind of controller and what mechanism has to be built. Now, when we talk about these batteries, there are different types of batteries which are used in electric vehicles. I think you all are familiar, isn't it? We have lithium-ion batteries, nickel metal hydride batteries, lead acid batteries, hydra capacitors, and recycling batteries. So, which is the most widely used battery in the electric vehicle? Lithium-ion. Why it is very widely used? Because it has high energy density. Lithium-ion batteries are very widely used in electric vehicles because they have high density and the efficiency is more and recyclability. Because another major issue with electric vehicles is what we do when the battery life has what to say, obsolete, or when the batteries are obsolete or battery life cycle is over, how do we decompose those batteries or how do we treat that electronic waste. So they can be reused or they are recycled. They can be recycled and they can be used for domestic purpose. For example, they can be used in our UPS. The major challenges with the lithium-ion batteries, the initial cost is very high, and the cost as the battery cost increases, the cost of electric vehicle also increases. You must be aware compared to the petrol or diesel engine vehicles, the cost of electric vehicle is more because most of the investment goes on the electronic part, that is battery plus the other automotive embedded controllers. Then it also has an environmental impact because lithium it has to be, and we have different variants of lithium ion batteries. I will be just touching about those variants of lithium ion batteries which are becoming popular. And it will have like mining of this lithium, it will have an impact on the environment and recycling it. Though we say that they can be recycled, recycling is a tedious process. So there are both pros and cons, but still we prefer to use lithium ion batteries. So moving on to the types, in lithium ion itself, depending on the chemical composition, we have various types. One is nickel cobalt manganese. So this is very commonly used, and we also have lithium iron phosphate. They are used in Michigan and in Ford electric vehicles because these are lighter in weight. When they are lighter in weight, for example, for the urban area, wherein we will have a frequent hop on hop off, then we need to have frequent charging. So lithium iron phosphate, they are lighter in weight compared to nickel cobalt manganese batteries, and then they will give more mileage because of lighter in weight. So they are tried with in Michigan and in Ford vehicles. Then we also have solid state batteries. In the lithium ion batteries, what we will have three layers, anode, cathode, and then in between a separation layer will be there. In solid state batteries, we will have only anode and then the separating barrier. There will not be cathode. Therefore, they will be lighter in weight and controlling is easy in solid state batteries. But still, they are emerging batteries. This is not a fully mature technology. A lot of research is going on in solid state batteries where we have only an anode and a barrier, there is no cathode. So the other types of lithium ion batteries which are popular are lithium cobalt oxide battery and we have lithium titanium. So basic like this thing is we use lithium along with that we have the other chemical composition cobalt titanium and we also have lithium iron phosphate battery. Then we have lithium nickel manganese cobalt battery oxide battery. Then we have lithium manganese oxide batteries. So what is the pros and cons of these batteries and where they can we can have a look into those things. So now moving on to the selection of batteries. When we say car batteries, we cannot randomly put any type of battery. We have different batteries like that, the batteries which are available in different shapes, and depending on the shape, the capacity also varies, and when the capacity varies, their application also varies. We have three types of car battery. Cylindrical cell, which you can see here. So we have cathode, anode, in between there is a separator. As I said, in lithium ion batteries, we have cathode, anode, and then a separator. So in case of solid state, only this cathode will be there, the separator will be there, this part will be missing. So that will be like we will have a cylindrical structure. This is called a cylindrical cell, and we have prismatic type, and we also have a pouch cell. So these are the different types of like the different geometrical shapes in which the batteries are manufactured, and where what we can use depending on the size and capacity. So the cylindrical capacity varies from the battery capacity ranges from 2300 to 26,000 milliampere hour. So the lifespan is around 25,000 cycles. So these have more like lifetime and then the ampere hour compared to prismatic and pouch. The cost, also the cylindrical, the cost of cylindrical battery is less compared to the prismatic and pouch. Therefore, we could have seen many circular batteries which are connected. We will have a battery pack which will be connected, and then there will be cooling on either side in order to cool, and then there will be cell balancing. So each one we call it as a cell, and we try to maintain the voltage across the cell constant with different techniques so that they all will be charged at the same potential in the same time, and they will discharge at the same rate at the same time. So that is one area where a lot of work is going on, battery management system, where the active cell balancing methods are becoming very popular. So then we also have, apart from lithium ion batteries, we also use nickel metal hydride, that is NIMH batteries. They are used before this lithium ion batteries, and they have lower energy density, but still for small cars or small vehicles, we use nickel metal hydride batteries. And like lead acid batteries, this you must be aware, lead acid batteries, even now they use in heavy duty vehicles, isn't it? So why do we use lead acid batteries in vehicles? For lighting and for low power applications. Suppose if we have an information and entertainment system, in order to power up that, we will use lead acid batteries. But then we also have ultra capacitors that are then becoming popular because the power transfer, the dynamic power transfer is faster in the ultra capacitor compared to the chemical composition type of batteries. Therefore, the ultra capacitors also they are used as energy storage devices. So these are the various types of batteries which are used in electric vehicles, and most popularly used is lithium ion. And we also have some manufacturers with lithium ion phosphate. Maybe I have a small video I can share it later which I have taken it from um, Ford and this thing, manufacturers. To have a comparison between the lithium ion and the NIMH batteries, because these are the two variants which we are using at present. The primary uses of nickel metal hydride, that is NIMH batteries, it is an ideal in electric vehicles. And before the invent of this complete electric vehicles, we were using NIMH batteries. Now the transition is towards lithium ion batteries. The longevity compared to this lithium ion battery, the lifespan of this NIMH battery is more. Safety, these batteries are safer compared to the lithium ion batteries. You would have studied some case studies wherein the electric vehicles exploded because of battery accidents, isn't it? Because of that, you would have got fire and such. And also self-discharge rate. What is the self-discharge? Any idea? So if the battery is idle, when they are not in use, automatically they get discharged. It is like if you have a capacitor, if you don't use it over a period of time, complete charge of the battery capacitor would have got depleted here also. So that should not happen, isn't it? Because if the battery is idle, it should not get discharged. Because most of us, like, we may not use our vehicles during the weekdays, only when you just want to use in the weekend, and if you see the battery is still, that is not good. So for that, what kind of battery it is desirable, that we can see. So the self discharge rate in case of nickel metal hydride NiMH battery is more compared to lithium ion batteries, and the environmental impact, both whether it is lithium or NiMH batteries, they have hazardous environment, like impact on the environment. One is we do lot of mining. After mining, we make these batteries. After making batteries, how do we dispose this waste? So, and depending on the capacity and other factors, the comparison of various the battery types which I had listed, maybe for the lack of time, I'll skip this slide. The battery, based on the energy density, power density, life cycle, charge and discharge rate, because this is the one which will decide what will be the battery life, isn't it? So charging and discharging cycles. Then the thermal stability, that means the battery should not get heated up, and if they are heated up, then there have to be proper cooling. Otherwise, if the battery is heated up, it will take more time to charge the battery. So in that case, we will not be able to fastly charge the battery, the one which is heated up, because ICTE losses will be there. Then the recycle, with respect to the recyclability and capacity retention, the cost of various batteries, which I had mentioned in the earlier slides. So when a quick comparison between the other, like the major batteries which are used, one is lithium ion, nickel metal, lead acid, and sodium ion batteries. So this offers high density, but this is cheaper compared to this. Lead acid battery, it is cheaper, but energy density is less. So sodium ion batteries, they are going to be cheaper than all these types, and then the energy density will also be more, and control will also be faster compared to the other types of batteries, but they are still not still mature technology. So the other battery charging, battery technologies which are emerging, that is lot of research is going on: sodium ion battery, solid state battery, and lithium sulfur power sources. These are the batteries, like where a lot of research work is on. This research work is going on. Now, as per today's session, now with this brief introduction, choice of battery. First, we need to know the type of battery to decide which fast charging method we will be able to adopt. Now, let us discuss about what are the types of charging which are used in electric vehicles. So, when we talk about electric vehicles, maybe we can restrict only to two-wheelers, four-wheelers, not for heavy-duty vehicles, because the electric vehicle technology is not mature enough for the heavy-duty vehicles. We have basically three types of charging. You would have heard of it, isn't it? Level 1, level 2, and level 3 charging. What is this level 1, level 2, level 3 charging? Any idea? Have you heard? Yes. What is level 1 charging? So level 1 charging, that we can charge up to like the battery capacity, or it can take a load up to 1.4 kilowatt to 1.9 kilowatt. The battery rating voltage, it can go up to 120 volt, and the maximum capacity when the battery is charged, it can go up to 3 to 5 miles of range per hour. This is the speed at which these vehicles can be driven, and these cars or the vehicles can travel from 20 to 40 plus hours with a full charge. So here, like this is level 1 charging is the way we plug in at home and then charge a electric vehicle. Then we have the other type, the level 2 charging. Here you can see we go to the charging stations and charge, because this it will take a lot of time, isn't it? So it will take 20 to 40 hours in order to completely charge the battery. We do not have that much time or patience to wait till the battery gets charged, isn't it? Therefore, if this time has to be reduced, instead of charging them at home, what we do is we go to the charging stations, charge them. So in order to completely charge, it takes maximum up to 8 hours. So that is level 2 charging. And we can charge the voltage rating is slightly higher, that is 208 to 240 volts. So these this will be installed maybe in the apartments or in the public domain. That is the charging stations. Then we have the other type of charging. It is like the way we have C type, D type chargers for our mobile phones. The way is ultra fast charging method that is called as level 3 charging. The charging time actually it will take only 20 to 30 minutes maximum half an hour in order to charge up to 80% of the battery. That is SOC can like up to 80% it can be charged in 20 to 30 minutes. After that what will happen is if you be when SOC reaches 80 to like 80% to charge the battery from 80 to 100% it will take more time than with respect to the battery characteristics we will see. The voltage rating of these batteries will just it is higher, that is 480 volts, and the charging load will be higher compared to these two, level 1, level 2. And this is the one which is very widely used, that is fast charging. You would have heard of DC charging, isn't it? DC fast charging. There is not a one which is going on this level 3 charging. So these are the existing methods, level 1, level 2, level 3. Level 1 it will take 20 to 40 hours for charging. Level 2 in the charging stations it will take at least 8 hours, and then here it is less than half an hour. So these are the typical charging methods which are available, and the future is going to be like we have the Tesla superchargers which will take 20 to 30 minutes like the DC fast chargers. Then wireless power transfer, that is the electric vehicle batteries which are wirelessly charged when they are moving on the road. So that which uses inductive power transfer. Then we have battery swapping. Battery swapping is not a charging method. We just go and exchange the battery in the charging stations. Then we will be able to book the slots before we reach using some AI tools or AI algorithm. And once it is being booked, we will be able to swap the batteries. And then in order to go for what to say green energy environmental to reduce the carbon dioxide emission instead of depending on the power supply from the grid in order to reduce the burden of the grid, we can have the electric vehicles, the electric vehicles which are charged using the solar power. So that is the solar charging. Typical solar charging in the stations are available. So we need what are the other see now if you look at level 1, level 2 and level 3 charging, this is the one which everyone prefers. Then how do we achieve that? We need to have a mechanism in order to charge a battery quickly. How we will be able to do? Now if we have a look at this thing, we have various charging methods in order to reduce the time taken to increase the SOC of battery at least to 80%. Those what are the methods which are available? One is constant current charging, the constant voltage charging. Then we have other improved method over the constant current and constant voltage charging that we call them as pulse charging, boost charging, constant current, constant voltage, that is CCCV charging, and we also have multi-stage charging. We will have a quick look into what these charging methods are. And apart from that, what we can do is these are all based on the control technique, how we model like how we control the charging of the battery using the controllers or the power converters. So instead of controlling them, what we can do is we can use the mathematical model, and with that we will be able to control the charging the time required for charging batteries. Those are model-based charging methods which are used in order to reduce the charging time. We have two types in that. So one is electrochemical circuit model based, the other one is equivalent circuit model based. Then apart from DC charging, when we talk about when we talk about charging, battery charging, which is a supply which we need for charging the battery, obviously it is DC, isn't it? So all these methods we focus on DC charging. Apart from DC charging, now the trend is also on AC charging. We can use AC, may not be directly AC, a DC which is being controlled with the help of a converter, that is an inverter, and which is used in order to charge the battery, that is sinusoidal charging. We will just have a look into what is sinusoidal charging is or AC charging is, and how it will we will be able to charge the battery quickly. Now, before we move on to now, our main focus is on we need to reduce the time which is taken to charge the battery. So one must be aware of how the charging and discharging characteristics of batteries. Now, if you look at this is the charging characteristics. What we can see here is, so when you start charging the battery, what will happen? You will have a look at this. The current it is in, sorry, the voltage it is increasing. After some time, the voltage is becoming constant. So now, if you look at this initial part, what is happening to the current? The current is high. So when the battery voltage reaches certain threshold, maybe it is depending on the voltage or it can be depending on the SOC. Both the mechanisms are used that I will discuss in multi-stage fast charging control. So here if you see in the beginning, if you want to charge the battery quickly, then we need to pass higher current while charging the battery. But what happens if you pass very high current for longer time, the battery will get heated up, therefore the battery resistance will be high. So if the battery resistance becomes high, that is the temperature also increases. As the temperature increases, we will not be able to charge the battery quickly. So therefore, in the constant current control method, what we do is we will pass a high current for some time till the SOC of the battery reaches 80%. After that, the current is gradually reduced. That is constant voltage, constant current control of the battery, which is used for fast charging. The other method is what we can do is once the battery is charged like with the constant current, that is high current, when SOC reaches 80%, after that there is no point in maintaining the current high because it will add on losses and it will prolong that 80 to 20, 100% is more time, take more time to charge the battery. Then we have the tested in simulation also to rise from 90 to 90.5%. It was taking nearly like 20 minutes for us, more than that. So there is no point in maintaining high current when SOC reaches. In that case, what we do is we will allow the current to decrease, the battery current. So when we say the battery current should reduce, we should have some mechanism on the controller such a way that you monitor what is SOC of the battery. When SOC of the battery reaches a particular threshold, then you need to allow the current to decay. How we can allow the current to reduce? How it is possible? Our input is constant, right? If the current increases, the input power is constant. If the current increases, if we want to reduce the current, what is the alternative? We have to increase the voltage, isn't it? Therefore, from 80 to 20% of the SOC is always better to maintain the voltage constant rather than focusing on maintaining the current constant. How do we maintain this current constant? We just need to have a closed loop controller wherein we will take the current as the reference, whatever this current magnitude which has to be maintained, that has to be set as a reference. And when SOC comes to this 80%, this current has to be gradually reduced. How we reduce this current? By adjusting the duty cycle of the converter, which is used in order to charge the batteries, isn't it? So now battery discharging is not directly done, isn't it? We have power converter interface. We have various types of power converters and control mechanisms which are used in the battery technology. So we need to adjust the pulse width such a way that the current will decay. Once SOC reaches 80%, then we need to maintain the voltage constant so that we will be able to charge the battery quickly. So now combine these two advantages. In the constant voltage, what we do is the voltage will rise when SOC reaches some percentage. We try to maintain the battery voltage constant. To maintain this battery voltage constant, again we need to have a closed loop control loop wherein this voltage will be given as the reference voltage. Any idea what voltage magnitude should be? That should be equal to the rated capacity of the battery. If the battery is of 12 volts, this has to be the 12 volts reference that will be given, and with respect to that, it will try to maintain the voltage constant. So now the advantage of this constant current that will be combined. That the type of technique we call it as constant voltage, constant current, that is CVCC, or in the literature they would have also used the name interchangeably, that is constant current, constant voltage charging method. So what we do in this constant voltage, constant current, as or as I said, it is constant current, constant voltage. Both the names are used interchangeably. First, we try to maintain high current. When SOC reduces reaches certain threshold, then what we do is we will allow the current to decay. We will switch to constant voltage here. So the transition will happen from current control to voltage control. At this point, we will cut off this current control. So that is known as CCTV, and this is more advantageous compared to constant voltage charging or constant current charging. And this is the widely used, as of now, it is the very widely used fast charging method in the electric vehicles. Even we had worked on this constant current, constant voltage charging, and we have explored the results in simulation. The other fast charging techniques which are available now, as I listed in the previous slide, multi-stage charging current, and then pulse charging current, constant current, pulse charging current, and bidirectional pulse charging current method. These are all various pulse charging methods. So this is one other thing which we had developed, like the circuit which is used for fast charging of electric vehicle. We had used bidirectional circuit and zeta converter, which will act as circuit converter in the power loop. This was for electric vehicle to grid to vehicle operation. We had the transition from grid to vehicle and vehicle to grid automatically happening in the circuit depending on the SOC of the battery. If the SOC is greater than 80%, the battery can put discharge, and if SOC of the battery goes less than 30%, we had set the threshold 30 to 80% so that the battery will get charged from the grid supply, that is grid to vehicle, vehicle to grid mode. And in this, we had adopted the fast charging method, that is CCCV fast charging method, which was used here. Using this semi converter is more beneficial because we will be able to maintain the supply power factor. We will be able to improve the grid power factor because setting it has an inherent advantage of boosting the power factor. It is used as one of the power factor correction circuits. So and here matrix converter we have because for vehicle to vehicle this should act as equivalent rectifier, and then LCL filter that is used for vehicle to grid operation. We had taken the reference values of this bidirectional zeta converter, that is given to fuzzy logic controller and the PWM generator. This will help us in controlling the battery charging, that is either we will be able to maintain constant voltage or constant current based on the time based or SOC based transition we had used. So these were some results which we had got, like SOC, when SOC was very anticipating to write anything, and we wrote fast charging. When we were trying simulations, it took more than 20 minutes. Then what is the current here? You can see the negative current indicates battery is charging or discharging. So if you see the voltage of the battery, here it is rising, the current is decaying. So whether it is charging or discharging, P is equal to V into I. This is positive, this is negative. So discharging. And the transition from constant current to constant voltage, we have configured the current the controller such a way that it will switch from constant current to constant voltage mode default by looking at or by sensing the current and voltage magnitudes. So with fast charging, we were able to reduce the time taken to charge the battery. That is conventional CCCV method, which combines the advantages of constant current and constant voltage control. The major drawback of this CC or CV or CCCV method is we maintain the current high for long duration, isn't it? When the current is maintained high, then there will be losses in the circuit. Thermal management of the battery becomes more challenging. So because the thermal management becomes more challenging, what we do is we go order to reduce the temperature rise, and because depending on the temperature, the charging current will also get affected. So we need to maintain the temperature. So that what we do is, instead of maintaining this current pulse high to longer duration, what we do is we control this current pulse. So the current, if you see here, it is a step waveform. Initially, till the battery like voltage reaches certain threshold level. There are different approaches which are used. One is based on the exposure, or it can be based on the voltage level. We maintain high pulse current pulse only for a short interval of time when SOC reaches level, let's say some percentage. After that, when that is being set, that SOC, like let us say it moves from 30 to 40%, then the current level is gradually reduced. So in that way, we will be able to reduce the current, the charging current, and its impact on the battery thermal management. So this type of charging, it is called as multi-stage charging. Current, this is also one of the fast charging method which is used. So this will significantly reduce the charging time, and the efficiency of this charging method is also better compared to CC, CD, those three methods. And the temperature wise, it will be within the limit, and the battery, the stress will also be reduced, and battery will have an extended life. So these are some key benefits of using multi-stage charging. So coming to multi-stage charging, if you see, there are various approaches which are used in multi-stage charging. Here what you can observe is we have a current pulse. If you see here, the current is reduced, but the step size, if you see the time interval, it is at equal interval, isn't it? So that means we can have a timed operation. If let us say that we will allow, let us say that SOC we will give in three steps, 10, 20, 50%. So for that, the time taken may be like let us say 3 seconds, 5 seconds, 10 seconds. So based on the time, if you send, and then based on the time interval, the current magnitude can be adjusted. That is one approach. And here you can see based on the SOC of the battery, the current is being stepped down, or it is being decreased. So we have various approaches in this multi-stage charging current. Those approaches are listed in these waveforms. So one is, for example, if the battery has to be charged, like let us say that you have fixing three SOCs. Based on those SOCs, when the battery SOC reaches that percentage, we reduce the current. So all this is done with the help of sensor and control action. So we need to develop a control mechanism such that when the SOC of battery, like let us say that it has increased when SOC raised to 40%, then the current is reduced. So now if you see that step reduction is equal. So we have other approaches which is with respect to the time, and instead of using SOC, we can monitor what is the battery terminal voltage. When the battery terminal voltage rises, we can to certain thresholds we can reduce the current. For example, like let us say that we have a lithium ion battery of 5 volts. Let us say that initial battery voltage is 3.2, and when the battery voltage is 3.2, maybe the current, let us say that it is equal to 3 ampere. When the battery voltage rises to let us say 3.4 volts, that means we need to raise the voltage. When the battery voltage goes to 3.4 volts, this current will be reduced to let us say 2.5 ampere. Again, when the battery voltage increases to let us say 3.6, the current will be reduced by another 0.5 ampere. Like this, based on the battery terminal voltage, the reduction in current happens. Basically, instead of maintaining a constant current pulse for longer duration, we will go for pulse current in case of multi-stage operation. The other one is here, which you can see is, let us say that the battery is charged from 30 to 40%. Then this is the kind of hysteresis which you can see. Then what we will do is, here if you see what is happening to the voltage, when the voltage reaches certain threshold, then the current is reduced. The battery will start decaying, that is the battery is discharging. When the battery voltage comes down to a certain level, again what happens is, the current will be maintained till the battery voltage increases to certain level. It is like we allow the battery to charge. When the battery is charged, Then when that particular threshold of the voltage is reached, the current is cut down. After this current is cut down, what happens? The battery voltage will come down. So now if you see here, the battery voltage is coming down. After that, again the battery voltage will increase. Till then, this pulse duration has been maintained. This di by dt, dv by dt, dv by dt will be equal to 0. Because at this instant there is a sudden like what you said, steep reduction in the voltage. Battery voltage will rise and then the voltage, it is like you can imagine on-off controllers. In on-off controllers, what we will do like when we reach certain threshold level, the switch will be turned off. Again, by default, the voltage of the output will come down. When the output comes down to certain minimum level, again the like the what we will turn on the switch. That is on-off control. This is based on the cut-off voltage based transition. Basically, we use on-off controller for this. Mainly to reduce the thermal issues. Actually, when we reduce the thermal issue, we will be able to achieve fast charging. Maintaining the current for longer duration is of no benefit because we will not be able to enhance or reduce the battery charging period even if you maintain the current high all the time, because once SOC reaches 80%, battery will get heated up. And we need to allow the battery to cool down, because when the battery is heated up, even if we try to charge, you would have noticed the same issue in the mobile phones, isn't it? So when we have normal charges, even if you plug in for 1 hour, it would not have charged for more than 50-60%, isn't it? That is due to this issue, maintaining the current constant, because we are giving constant current. Because of thermal runaway, it is not able to. Why this will happen is when you keep the lithium ion this thing, it will develop a kind of plateau when the current is low. I think I have in some slide that by default the voltage of the output will come down. When the output comes down to certain minimum level, again the like what we will turn on the switch, that is on off control. This is based on the cut-off voltage based. Basically, we use on-off controller for this. Mainly to reduce the thermal issues. Thermal issues. Actually, when we reduce the thermal issue, we will be able to achieve fast charging. Maintaining current for longer duration is of no benefit because we will not be able to enhance or reduce the battery charging period even if you maintain the current high all the time, because once SOC reaches 80%, battery will get heated up. And we need to allow the battery to cool down, because when the battery is heated up, even if we try to charge, you would have noticed the same issue in the mobile phones, isn't it? So when we have normal charges, even if you plug in for 1 hour, it would not have charged like more than 50-60%, isn't it? That is due to this issue, maintaining the current constant, because we are giving constant current. Because of thermal runaway, it is not able to. Why this will happen is when you keep the lithium ion this thing, it will develop a kind of plateau when the current is more. I think I have in some slide that plateaus. A small image I have clicked. What happens is this kind of plateaus, that is the lithium deposits will grow like a cactus if the current is more, and if this is being maintained like several for cycles of battery charging and discharging, this composition grows more and more. So this will act as a barrier for fast charging. It is like you have a spike inside, so that will not allow the battery or the movement of carriers. Basically, we try to maintain. Fast charging is all about maintaining voltage and current of battery at a specific proportion, so that either the battery will get heated up, or we need to have a transition separator based on SOC. We need to monitor the current and voltages. If that is done, we will be able to control. Same thing is done in mobile charges. These are the various variants. So here what we will do is when the voltage reaches a certain threshold, we will cut it off. When it comes to certain minimum level, again we will turn it on. So a kind of on-off controller, that is also one of multi-stage boosting the speed.
What will be the life of the charger?
Our life, it depends on how many charging and discharging cycles we have, and lifetime it depends for various batteries I have listed here, like charging and discharging cycles. The life cycle of battery will be like for these.
Charger, because there is pulsating current flow and voltage.
No, everything it is controlled. Because when we are able to control those currents, it will not have any negative impact because all these are controlled using our power converters. So to put it in this thing in with the help of a power converter circuit. So due to which we will draw only the required amount of power, there is no wastage of current. So only that much current is drawn from the supply. So the efficiency of the circuit will also, the battery will also, charging this thing will also be high. So
model size gets bigger, the model gets
no. We will be able to reduce the size because they will become very compact in nature. See, if it is conventional rheostatic based approach, what will happen? Our input is fixed. Whatever we are giving to the load, we try to adjust the load inputs based on by adjusting the resistance value.
But you are varying both the voltage and the current. It is not only the current. There is marginal variation in voltage. Along with it, there is marginal variation in current.
Yes. Then only we will be able to control the charging period of the battery. See, voltage, it is with respect to what we are doing is why it is being projected in terms of voltage. Actually, it will be with respect to how we measure the voltage, it will be with respect to state of charge of battery. How much the battery is charged. Like let us say the battery is charged to 50%. That means if the battery rating is like let us say that it is 1 ampere hour with a voltage of 5 volts. If the battery, SOC if the battery is 50%, then we will be able to get terminal voltage of maybe like 50% or less than that. That means if the battery rating is 1 ampere, then maximum voltage what you can get from that battery will be just 0.5 volts. So we try to relate with respect to SOC of the battery.
Will have any relation with CAT and state of health related to this parameter?
Yes.
How will it play impact in this case?
Which one?
Very point for cutoff voltage based on transition.
Cutoff voltage based on transition. Actually, how we define? See here, depending on, see these are all the multi-stage operation. Maybe with respect to this slide, I'll explain. This is with the continuation of that multi-stage pulse current, whatever we are using. For different battery types, we define different ways. For example, if it is NCM battery. So if it is NCM battery, here if you see, there are only 3 charging states which are defined, that is SOC percentage. So from 0 to 70%, it will be defined. If this is NCM battery, the transition should happen at 3 stages. So when SOC reaches 70%, then SOC from 70 to 80%, then SOC from 80 to 100%. So when these ranges are reached, the current magnitude will be adjusted for this kind of battery. Now for that battery, if you see, we will have only 3 currents. So this current transition will happen when the SOC is equal to 70%. This current transition will happen when the SOC is equal to 80%. This transition will happen when it is equal to 100, it will completely degrade. So now, this, if you see the number of pulses and volts in it, this is for this type of battery. So here, for different batteries, we will define when the transition has to happen. These are the standard practices in the industry which are used for multi-stage topology. If it is NMC battery, when SOC reaches 20%, they want decay the current. And when it is being 20 to 40%, then the second decay. Then 40 to 60%. These percentages, they vary depending on the type of battery, and that will be defined by the user. So how you define the transition you will be able to. So for different batteries, different types of batteries, these are the standard practices which they have defined. Depending on that, we will have a cutoff or reduction in the currents at these stages. When SOC reaches these voltage levels. This is based on SOC. Similar to that, the battery manufacturers would have preferred, for example, if it is lithium phosphate battery, instead of taking this is completely like this is for one approach I have listed. So we have 4 different approaches, isn't it? This is for SOC, this pattern which I had. So this is very common practice wherein generally only 3 SOCs will be taken, one on the lower range and one from 40 to 60, one is above 70%. They define those 3 time intervals. That is based on that. At these times the transition should happen. The current should reduce, like it will be defined. For this approach, whatever it is, we will say in the next slide. So similarly, at what stage these transitions should happen based on the voltage, that depends on the type of battery what we use. So that is the reason I just try to cover the types of batteries and their composition, lifetime, advantages and disadvantages in the various beginning loads. That is one type of charging. So we have another type of charging which is called as pulse charging current, and we have different methods in pulse charging current protocol which is used. Maybe straight away I will just move on to this. So in the multi-stage approach, what we were doing, we will start with the high current and we will reduce the currents, isn't it? In pulse charge current, instead of reducing the current, what we do is we try to adjust depending on the frequency. And the frequency at which the battery can be charged, that is through the switches we will charge the battery. So otherwise we will not be able to maintain constant voltage or constant current as per our requirement. So in that, what we do is we go for different pulse current approaches. This is based on the positive current pulse. If you see here, we will increase the current and then the current will be there for a smaller, this pulse width it will be defined by the user, and this pulse width it also depends on the frequency at which we are charging the battery. So here we will have on off, this kind of charging we call it as pulse charging. Basically it is PWM based charging. Now if you maintain the, either we can maintain this current pulse width of these currents constant. That is based on the constant width we can have, or we can have the current width which is varying. This is also a kind of pulse charging. And here if you see in the first 2 cases we have the amplitude which is constant, but the ondulation is varying. So we have another approach which is in which you can see here we have the equal width, that is on period is same, but the amplitude of the current is reducing. So with this approach, like when you try to decay the current over a period of time, we will be able to reduce the deposition of lithium ion in successive operations. So we will be able to maintain that fast charging. So then here, this is a kind of level shift wherein the current will be varied, the magnitude will be varied between 2 intervals. So high low, we will have, it is like level shifted PWM pulse. In this way, we will maintain the current, this current is used in order to charge the battery. This is also kind of approach wherein the current will be maintained between higher and lower limits, but it is level shifted. And here if you see, so what is your observation? We have constant width current, but here if you see the dead period is varying. After that, we maintain the current of constant pulse width for certain duration. After that, if you see the amplitude, it is the variant of this variant, the amplitude will be varied, but after varying, we are maintaining that amplitude constant for certain cycles. Again, if you see, we will have a dead period. After that, the amplitude is reduced. This reduced amplitude is pulsed for certain interval of time. With this arrangement and with this arrangement we will be able to utilize, or we will be able to have a proper thermal management of the battery, which will enhance the lifetime as well as the charging period. So these are the different approaches which are used in pulse charging current. So we have pulse charging, a constant voltage protocol, wherein the voltage will be maintained constant and the current is really like this. We have the other approach like a pulse charging phase. What we do is here, we maintain the pulse constant. After that, instead of maintaining it zero, this will be gradually reduced. So with this approach, as I mentioned before, we will be able to.
This type of torque is being used in commercial.
No sir, commercially right now we are using still here with CCCD. We have not extended this. Work is going on. So these are all the ones which are available in the literatures, but practically they are not put into operation so far.
So this is a lot of research.
Yes, lot of research is done. In the they are not deployed in the vehicles, this kind of charging. But this is like more promising, this kind of thermal management as we can use. Only in Ford or some listing they have tried implementing this type of control. Ford vehicles. Still it is in the link. Whether it is wireless power transfer or solid state batteries, they are still in the research because EV itself is an emerging technology. Now we have this thing. So charging method still lot of work is going on. There is no major technology, and though these technologies are available, they have to be standardized. So across the globe, if they say that like okay, the vehicles of these types they have to use this kind of charging, that mandate has to be made the way we have for IC engines. So that regulations are not made for this EV charging. The regulations have to get to be framed. What kind of charging for which type of vehicle, for what capacity, that it has to be decided by regulatory authority. How many minutes I have? Just 5 minutes I try to wind up. So either we can have unidirectional current and so we have constant current pulse charging wherein we maintain constant current. After that we will switch to pulsing of current. With this we will be able to achieve these benefits. So full charging without overcharging, complete the process safely without getting these things. Then we can have bidirectional current. Earlier we have seen current was only the positive current. We can have bidirectional current, and then we can also have this kind of current which is both alternate. We will have positive current, then a dead period, then negative current. These bits can also be adjusted. That is one. And instead of positive this thing, we can also have negative pulse charging. This is called as bulking. What is bulking with this? We will use positive current, and then we will have a negative spike of current for a small interval of time. So that when we have that negative spike, it will help to reduce the thermal what is heat dissipated, and again we will give positive pulse. So this is also from white paper from some battery manufacturers which are used in this thing. I have shared the respective links if somebody is interested. Research is going on in this field. Then thermal management, what we try to do is based on the temperature we try to adjust the current. That you can see 1C, 2C. If the temperature is less, then we try to maintain the constant current for longer time. If the temperature of the battery is high, we are trying to reduce the current. So this kind of approach is called as thermal approach. Sense the battery temperature, but to sense the battery temperature and then have proper control state. It is a way we cannot make like what to say. We do not have a temperature sensor which can sense IC engine temperature. That is combustion chamber temperature. It cannot be made like what to say measured exactly. We use indirect approaches to sense the IC engine temperature. And likewise here also battery temperature, if it can be sensed and we try to maintain this temperature, the The optimal range for lithium-ion battery is from 15 to 40 degrees centigrade. So try to maintain the temperature. Without temperature rise, if we can charge the battery, then we will be able to charge it quickly. So now what is next is model-based approach. I will just with you. So instead of using this current or voltage-based approaches, what we do is we go for mathematical modeling of the battery, and with that we try to control the current and voltages. We have two approaches. One is electrochemical model. So they use a high-level model of the batteries in order to control the current. And the other one is like it is similar to Thevenin's equivalent circuit. You can model the battery by its equivalent Thevenin circuit, and that modeling can be used in order to the way when you have an equivalent circuit, we will be able to know the time constant, and if you want to reduce the time constant, what should be the input and current magnitude, that we will be able to decide. That is equivalent circuit model. And data-driven model, so we use many of the machine learning models in order to find it, okay, if this is your current, how much time it is going to take. So like that we can decide based on the current level how much the time will be. So based on that forecasted or the estimated values of the time, we will be able to decide what can be the current magnitude. We had done a lot of work on this data-driven model. We have taken like battery details from the NASA website, a lot of battery specification details are available. This is like those who work on the battery management life cycle estimation. You can take those data. Based on the data, we have tried analyzing what will be the life cycle of the battery, and then how much time they need to take to charge the battery. That is data-driven approach. And then sinusoidal method, that is AC charging. AC charging, what we do, we will have DC, then we will have high frequency inverter. So this inverter output is it will be used in order to charge the battery. We have different converter configurations which are used for sinusoidal charging. If somebody is interested, I have slides on that. I will share it with you. Then what are the trends in EV charging? This one is we have wireless power transfer. So what is wireless power transfer? That like the primary coil is in here, transmitter coil, receiver coil. We know how everything works. We have various converter configurations which can be used. Only the thing is the distance between these two coils, that is transmitter and receiver coils, it should be like based on the road clearance level of vehicle. So we have taken the scenario Indian vehicle system where the road clearance will vary from 11 centimeter to 18 centimeter. For all SUVs, it is like about 18 centimeter, and we had an arrangement wherein we will be able to vary the distance between the transmitter receiver coil and wirelessly charge. So how to yes sir, this is basically for charging. When the vehicles are moving, that time they can be charged. Then there is no need to spend separate time for charging. This is for onboard charging. So these are like what to say, still in the development stage. So we were trying to develop one converter. Sir, we have like still it is like Mitsubishi, they are working on that, and we were trying to develop this approach for Nissan Micra. Practically they are not put into operation. They are in the testing stage, wireless power transfer. For Nissan Micra, we have developed this architecture, the control like wireless power transfer, and we had developed like the height between the transmitter and receiver, which can be varied. This is the transmitter coil, we had taken the receiver coil, and based on the row clearance, we adjusted the side. And this is what the prototype which we had developed, that is wireless power transfer for electric vehicles on road like moving, and with the solar system. So at the receiver, we could take only a maximum of 5 volts peak to peak with the 11 centimeter distance, that is what to say, road clearance level. So this one we have patented also. Another method is battery swapping, and then there are also like what we say, lot of now we are what to say, applying lot of machine learning AI techniques in order to manage the battery, that is in the battery management system. All these are mainly the data-driven approaches. charge. Maybe I thought I will demonstrate some simulation, maybe due to lack of time, or if circuit during this time after this session. We will see from wireless power transfer with constant current, constant voltage charging. If you can give us some time, we can simulate and check how exactly it works. If it is without that control technique, how much time? Maybe like S4C will try to limit from very small range, maybe 5% variation. So how much without control technique, the time it is taken for charging, with CCCV, how much time it is going to take, that we will be able to see the clear difference, that is reduction in charging time with respect to these control approaches. These fast charging techniques are not limited only to these methods. These are very popular one, still maturing technology, I can say.
So recently, US NASA has successfully tested the wireless charging for analysis about 3 kilometers. So
See, it is still in the research level. Practically, they have not put it on. Means whatever we have demonstrated, but they have not standardized. So even whatever we could see here, what we have developed, we were able to deliver like developing the same transmitter receiver point. But standards and all those things and the regulations are not yet established. They have tested. Even like Mitsubishi, they have tested this wireless power transfer, but not on large capacity. Maybe if there are any questions, I can take it.